I'll just give like a quick introduction. Basically, I'm very excited to introduce Mr. Tom Mueller, who is the co-founder and Chief Technology Officer of Propulsion at SpaceX. He's the champion of the Occupy Mars movement, which I am proudly representing on my shirt, and the brains behind SpaceX's rocket designs. As one of the world's foremost rocket engine designers, he is responsible for developing propulsion systems and engines for both the Falcon launch vehicles and the Dragon spacecraft, and much more, obviously. Before we start, I just want to say thank you from all of us for taking time out of your busy schedule to talk with us. We are all very amazed with the work you do at SpaceX, and congratulations on all the success you guys have been having with the recent launches.
Well, thank you.
Sweet. So basically, you can take it away. If you want to. Do you have anything?
Did everybody see that launch yesterday?
Yeah, I watched the launch. Did anyone else watch the launch yesterday? Yeah. Yesterday morning? Yeah, that was pretty cool.
Saw it on Reddit.
Okay, so let's go ahead.
Yeah, if you want, if you have like a talk prepared, and we have some questions at the end.
Okay.
Sweet.
So I'm going to talk about low-cost access to space. When I was a kid, in the 60s, I used to watch Star Trek, and I was 8 years old when they landed on the moon. And of course, I think like a lot of us, we thought, 50 years from now, we'll be on Mars, we'll be traveling maybe to, other planets, have more of a Star Trek-like experience. And, it didn't really happen, did it?
Right.
The invention of modern rocketry until they put a man on the moon was about 40 years, from Goddard to Armstrong. And, it's been over 50 years since then, and it seems like we haven't really achieved all that much. In fact, we no longer have the ability to put a man on the moon right now. We don't have the hardware. So why is that? And I think one of the big reasons is it's still prohibitively expensive to get to orbit. And why is that? It's because rockets are very expensive. The mass of a rocket is about 95% propellant by weight of a Falcon 9 rocket. So is it the propellant that's expensive? No, actually it's not. It's less than 0.5% of the total cost of the rocket is the propellant. It's the structure of the rocket and the engines that is very expensive. And the problem is we throw these rockets away. Until very recently, that was just the way that you thought about rockets, is they're expendable, because they're originally developed as intercontinental ballistic missiles, and of course that's not reusable, so nobody ever really thought to make them reusable. And so it's the only form of transportation I can think of where people don't think of it as being reusable. They just think of it as expendable. Like, can you think of anything else that you would throw away after one use, that a form of transportation? The only thing I could ever come up with that's sort of like that is like a top fuel dragster. They make one run down the quarter mile, and then they have to rebuild the engine. And when you design that way, you can do incredible things. Those cars do a quarter mile in less than 4 seconds, and they're doing over 300 miles an hour at the end of a quarter mile, or actually 1,000 feet now they run. So it's pretty incredible when you build something. You design it for single use, you can really push the bounds of engineering and get incredible performance, and that's true with rockets. If you make a rocket reusable, you have to give up some of its performance, just like your family car can be used tens of thousands of times and drive hundreds of thousands of miles, and it doesn't have near the performance of a top fuel dragster, but it's affordable and it's very useful. So we got to find something in between, something where we have close to the performance of a top fuel dragster, but somewhat closer to the reuse and utility of like a household car. So what we need to do is design rockets to be reusable. So that's what we set out to do. And first of all, you got to make the rockets, relatively low cost. If your rocket costs $1 billion, even if you use it 100 times, it's still going to be very expensive to use. So we set out to build low-cost rockets right from the beginning. The cost that the government cost-plus programs charge for their rockets is just ridiculous. We don't compare our costs to any space vendors, any government-subsidized space vendors, because it's not a good starting point. What we try to do is compare our costs to commercial products. Like even airliners are kind of expensive for our cost trade. So I always get from Elon. I always get the, you know how much it costs to make a Model S Tesla. Start from there and work my way up to the rocket. Like here's a conversation I had maybe about 5 years ago on a Merlin 1D when we first developed it. He asked me. He said, how much do you think it costs to make a Model S? And I'm like, I don't know, $50,000? He said, no, about $30,000 is a marginal cost to produce that car. And he goes, how much does that car weigh? And I said, about 5,000 pounds. Right, about 5,000 pounds. He goes, how much does a Merlin engine weigh? And I go, about 1,000 pounds. And so he's like, so why the heck does it cost, some fraction of $1 million to make a Merlin engine? And I mean, he has a good point. So he said, I'll give you, the materials that you use are not aluminum, they're not stamped, so I'll give you a factor of 5. So it's equivalent to a Model S. It's, equivalent to, say, 5,000 pounds of rocket engine. So why is it, 20 times the cost? So that's kind of the way that we look at it and the way we think at SpaceX, trying to get the amortization cost of the rocket down, because once you start reusing it, then it's really the big costs become the amortization cost of it, and the operational cost, and the fuel cost, which is basically the same model as an airliner. And we looked at that. The airliners are, they're about 50% operation costs, and I think it's about 20%, 25% amortization cost of the cost of the $300 million aircraft over its life. And so that's kind of the modeling that we want to do to figure out how to make access to space very affordable. So, like I said, we don't use we don't use space. We avoid space vendors like the plague. Like when we started developing the Merlin engine, I needed valves. I needed liquid oxygen and kerosene valves that had to work. So I went to some of the vendors that supplied these valves and said, hey, can you give me, a good price on your existing product? And no, they couldn't. So I said, can you design a much lower cost one? So they came back and said, well, you already know if it takes them like 2 weeks or a month to give you a quote, you've already got the wrong vendor. Like, if it takes them that long to just give you a price, how long does it take them to build the actual part? So they come back with hundreds of thousands of dollars for their part, and it's going to take 18 months to develop it. And I'm like, no, I need it like in 3 months. And they kind of laugh at you. So we ended up developing our own components, our own valves, pre-valves, main valves. We'd already developed the ejector and the combustion chamber and the main parts of the engine, but we were hoping that we'd just go buy some of this other stuff from existing suppliers. And no, the cost and schedule just wouldn't close for us. So started anybody that provides space hardware to government contractors is just not at the performance level we want to be at. So that's how we get the cost of the hardware down. Also, we had to have control of our own test site. So we developed a test site in Texas and did our own testing, because a huge cost of developing and testing rockets is the test site costs. So we need to get that under control. In my previous career, when I was at TRW, we ran an engine. It was a big engine, a 650,000 pound engine, but it was very simple. And we ran it at a government test site, a NASA test site in Stennis. And they had a crew of 100 people. basically. They had 2 shifts with about 100 people. And when we ran an equivalent complexity engine, maybe not that size, but like a 40,000 pound engine at our site, we could run it with like between 5 and 10 people. So that's what I was looking for running even a pump-fed large engine like the Merlin engine. It doesn't take an army of people to run an engine like that. And that, I think, the government contractors have convinced themselves it does. When I first started developing the Merlin engine, the conventional thinking was only governments can develop rockets. A private company can never have the resources. So it was SpaceX that kind of broke the ice on that and said, no, it doesn't take a government to do it. It doesn't take billions of dollars. It took us hundreds of millions, but it didn't take billions to do it. So you got to minimize fuel costs, because you get the hardware costs down. Now fuel is a major component of your costs. So you have efficient combustion, and we build our injectors are running at about 96-97% combustion efficiency. You really can't get much more out of a rocket injector than that. And use low-cost propellant. We actually picked the wrong propellant. It wasn't too bad, but we picked RP1, rocket grade kerosene, which at the time was $8 a gallon. We tried jet fuel, which is more like $2 a gallon, but it just didn't run very good. But very recently, we renegotiated the cost of the kerosene fuel, and I think we got it down closer to jet fuel. But really, what we found in more recent studies is that methane, natural gas, is the cheapest form of fossil fuel energy. That's what is mainly what they're getting rid of coal, getting rid of oil, and running on natural gas. It's the cheapest fuel that you can get, and it also has a great properties that it can be made easily on Mars. So that figures in too. But our next vehicle is going to be all methane fuel. Oxygen is a no-brainer. Oxygen is so cheap. Our cost for oxygen is about $70 a ton. So it's just almost free when you consider the cost. It's actually the fuel that's more significant cost. Even though there's more oxygen, there's 3 times as much oxygen on the rocket as there is methane, and 2.5 times as much oxygen as kerosene. It is by far cheaper because it's just so easy to make from air, from cooling air. So you get the fuel down, and then you got to make the rocket completely reusable, which we're still struggling with. When that rocket came back, like yesterday, it's smoking. It's sitting there smoking. We burn a lot of the ablative on it. We have to remove the legs in order to lower it and reinstall them. I mean, it's not a quick turn. What we want is like an aircraft. It pulls in. Pulls into the airport. The people get off. They fuel it while the people are getting back on. They do some checks. They do some inspections, and everything looks good. You go again. That's where we want to get to, and that's the Block 5 Falcon rocket that we're rolling out later this year is going to have reusable thermal protection on it, so we don't burn up the heat shielding on it. Yeah, it's got much better landing legs that just fold up and just drop the rocket, fold the legs up, ship it, fold them back out when it lands. So making it so it turns very fast so we can fly it. Our goal, Elon asked us to do a 12-hour turn, and we came back and said without some major redesigns to the rocket, with just the Block 5, we can get to a 24-hour turn, and he accepted that. All right, 24-hour turn time, and that doesn't mean that we want to fly that rocket, once a day. Although we could if we really pushed it. But what it does is limits like how much touch labor you can put into it. Like if you can turn a rocket in 24 hours with just a few people, then you're not spending a lot, optional cost, basically getting that rocket ready to fly again. So those are all the things that we did in order to get, or are doing in order to get the cost of access to space down. Hopefully by a factor of 100 when we do the Mars vehicle. We can't do that right now with the Falcon because we still throw away the upper stage. So maybe almost a third, about 30% of the cost of the rocket is that upper stage. It has a single Merlin engine on it, but a fairly sophisticated version of the engine, and also has the guidance computer and a lot of avionics on it. So it's a significant cost with the marginal performance that gets returned to launch site reusability and being able to throw some of the biggest satellites. We just can't make it close with that size rocket to recover the upper stage. We're gonna try in the next few years to start recovering the upper stage, but we won't be able to do it for all missions. So that'll help reduce the cost quite a bit. But the Mars rocket is meant to be completely reusable. Both stages. Gigantic rocket can put hundreds of tons into orbit in a single flight. It can go all the way to Mars and back. You have to fuel it on Mars. We need to make about 1,000 tons of propellant on Mars over a 2-year cycle to bring it back. That's a tall order. You need about half a megawatt to that much propellant to bring. But that rocket is going to be the real game changer. I would say the Falcon 9 is evolutionary, a reusable rocket that really reduces the cost of access to space. Maybe we can achieve a 10 reduction in cost over, like what ULA or the Russians or the Chinese are doing with the Falcon, but we want like 100 or more reduction in cost, and that's what the Mars rocket is going to do. That's going to be the revolutionary rocket. So once we're flying that, all other rockets will probably be obsolete. Luckily, Blue Origin is working on a fully reusable rocket. But we've really changed the industry. That the other guys are really scrambling. It's pretty funny to watch this because when we first started the company 15 years ago, my 15-year anniversary was Monday, yesterday, May 1st. So it's 15. We started the company on May 1st, 2002. Well, I started there. I consider Elon incorporated the company, I think, in February, but he didn't have any employees yet. So I consider when he had his first employee, he had a company. But anyway, over the 15 years, we've gotten this far, and when I was first hiring people, that's when I heard that not enough money to develop this rocket. And then we built the Falcon 1, which had a single Merlin engine in it, could throw about 1,000 pounds in the low Earth orbit. And they said, okay, you guys were able to build a small rocket, but you'll never build an EELV, like an Air Force mission class rocket. And so we built the Falcon 9 and started flying it. And then, well, you'll never be able to reuse it, or you'll never be able to go to the space station. At some point, you just stop listening to it. And I think it's great. It's if people think what you're doing is impossible, then you're doing the right thing. Like, we still, you can find the YouTube videos online where people are critiquing our recovery and saying it was all basically photoshopped or CGI. That's pretty high praise when people don't actually believe what you're doing. So I think it's great. And we were ridiculed by the other big companies in the launch vehicle business. At first they ignored us, and then they fought us, and then they found out they really couldn't win in a fair fight because we were successful, and we were factors of 2 or 3 or perhaps even 5 lower costs than what they could do. So then it becomes an unfair fight. Where they try to destroy you politically or using other means, and then at some point they figure out that they got to do what you're doing. So there's a lot of talk with these other companies about how they're going to make reusable, recover the engines, recover the stages, come up with a much lower cost rocket so they can compete. There's no way that ULA would have considered buying engines from Blue Origin except for the pressure that SpaceX put on them. There's no way that that the French would have quickly abandoned the Ariane 5 and moved to the Ariane 6 design because of except for the pressure that we're putting on them. So we're really changing the world. The Russians are now saying that they're going to come up with a rocket that can beat SpaceX, which is entertaining because they've been working on their Angara rocket for 22 years and have launched it once. And suddenly they're going to come up with a low-cost one. But anyway, it's great that we're changing the paradigm and causing everybody else to think differently about how this is done. So once we do it and everybody else starts doing it, then what's going to happen? I think the transport problem has to get solved, and then the killer apps in space are going to appear. And we don't know what they are yet. It's like when the internet first came out, people go, what good is that? Like, people couldn't imagine what you're going to use it for. I think we can imagine a lot of things to use a very low-cost rocket for. And the common ones you see are, space tourism, of course, hotels in space. Bigelow has his inflatable hotels, and trips around the moon, which we have already got people signed up to do that. Resort on the moon, perhaps. Certainly Mars, that's what we're doing. We're looking to colonize Mars. Space mining, metallic asteroids could be worth, trillions of dollars. Resources on the moon, there's water on the moon. There's helium-3 on the moon. Of course, we need to get fusion working first, but if we ever do, helium-3 would be very useful. And of course, mining metals on the moon. Satellites, bigger constellations of satellites with lower cost rockets. I think there'd be a lot more done in space if the cost comes down by a factor of 100. Less running wires on Earth and just transmitting from space, which is what we're doing. I mean, the satellite constellation that we're developing is basically to put the internet in space. We want to put eventually equivalent to what is currently the current bandwidth we have on terrestrial, like on fiber, in space. So we can basically double the bandwidth of the internet that exists, and it would be everywhere. In fact, it would be better out in the middle of nowhere because you would have the satellites to yourself. If you were like in northern Alaska or middle of Wyoming or middle of the Sahara Desert, you'd have a great connection because you'd have all those satellites overhead to yourself. If you're in LA, it's really not going to help that much because there's 11 million other people using those satellites. But people out in the middle of nowhere are going to love it. And Google really loves it too. That's why they invested about $900 million, almost $1 billion into SpaceX, because we can quickly move what they call backbone. I think about 70 to 80% of what you pull up on your computer, the information, is stored locally. Like, if you're here in LA and you're pulling up some viral video, it's probably stored locally. It's not coming from wherever it was generated, and moving that information from city to city and place to place is called backbone. And the example that I got was if you wanted to move data from LA to South Africa, right now it goes across the US to New York, it jumps across the Atlantic to Europe, it travels down through the Middle East and down through Africa and gets to South Africa. It's a lot of server hops and a lot of latency. Gigabytes of data to South Africa. With our satellite network, it would just be line of sight across, straight to South Africa with low latency through laser links between the satellites. So that's what we're working on. And imagine if you had a launch vehicle that can put hundreds of tons of satellites equivalent in a single launch for just a few $1 million. It just completely changes the game. Then you start thinking about putting big satellites and hundreds of them up there, and being able to service them. It really changes the whole dynamic. So that's what we're working on right now. So the transportation comes first. It's just like developing the Western U.S. They had the covered wagons at first, which got people over here, but you really didn't enable development of the West until they put in the railroad. Now you could move tons of hardware and tons of people for low cost. That's what we need to build, is the railroad to space, basically. So that's what we're working on. We're just the we're just the transportation. Like colonizing Mars, we need a lot of help colonizing Mars. We want to provide basically the airliner ticket to Mars, but somebody else has to provide the rental car when you get there, or the housing, the food, just building up. When Elon says we're going to provide it, easy access to Mars, that means we're going to be able to move you there, but it's going to be up to other companies and other industries to help make that happen. So it's going to be a huge collaboration to make this really happen. So I'm really excited about what we're doing. We're kind of hitting the limits of chemical rocket technology. The new engines we're developing for the Mars ship are very high pressure stage combustion engines, getting all the energy you can out of fossil fuel propellants. 99% combustion efficiency, over 4,000 psi combustion chamber pressure, full flow. So all of the propellant goes through the main combustor. It's not an open cycle, it's a closed cycle. So all of the energy from the propellant is going to thrust. It's basically, you can't get any more energy out of a chemical propellant. You can get a little bit more performance if you went to hydrogen and oxygen, but the rocket gets much bigger and more expensive. So the sweet spot is not hydrogen and oxygen. A lot of people thought that. I did too. The original Raptor engine was hydrogen oxygen, until I did the studies that showed if you use hydrogen and oxygen, the rocket is lighter because the propellant's lighter, but the propellant costs more. The propellant is harder to make on another planet. It takes a lot more energy. And the rockets, even though it's lighter, it's actually bigger. The structure is bigger, and the engines are bigger. So it's actually costs more to make it, even though it's carrying less weight. And that you can look at that if you compare the Delta rocket to the Atlas rocket. The Delta is a hydrogen oxygen booster, and it's bigger. It's 5 meters in diameter, compared to the Atlas, which is like 3 meters in diameter. But it's actually lighter and it has a 650,000 pound thrust engine on it, whereas the Atlas has a 950,000 pound thrust engine. And the Atlas can throw more, can just throw a lot more payload. And you look at a Falcon 9, it's a small rocket, it's 12 feet in diameter, but it can throw a lot more than a standard Atlas. So using a high performance, low density propellant is not the answer. So we've gotten everything we're going to get out of chemical propellant. So we're looking actually a little bit at we're doing electric propulsion for the satellites, and we're talking to people about nuclear thermal. The NASA centers are working on nuclear. It's just prohibitively expensive to test because you can't. It's not like the 60s where you can just let fission product fly out of your rocket out into the desert. You now got to scrub it and clean it and capture it, which is super expensive. I don't think SpaceX could really afford to develop that rocket ourselves, but if NASA ever gets turned on to develop those test stands, we would probably want to jump in on that, because you can just about double the performance of a rocket to Mars compared to a really good, like a Raptor system, a really good chemical system, with fission, with nuclear fission. Theoretically, fusion maybe 10 times better, antimatter maybe 1,000 times better, but I think those certainly aren't going to happen in my lifetimes. Hopefully in your lifetimes. The warp drive's still a long ways away. We're stuck with chemical propellant for quite a while. So that was my ramble. That's about what I wanted to talk about today. So we can open up for questions.
Thank you so much.
Thank you.
Thank you.
We've collected a few questions. Can you hear me okay?
Yeah.
Okay, so our first one is, how far is too far for the rockets? The Mars Colonial Transporter was renamed the Interplanetary Transport System because it was deemed that travel could be made further than Mars. And similarly, do you think deep space travel will ever be possible, or are we limited by distance?
Yeah. I mean, some things are too far. Like you can't get to Mars with our system about 24 out of 26 months. You cannot get to Mars. It's on the other side of the sun, and it's just you want to go to Mars when it's coming swinging by the Earth. You want to go when it's miles away, not when it's 210 million miles away. We can obviously go to the outer planets like we have with the planetary probes. It's just that the way to do that is using gravitational assist, and it takes years. If we want to go direct to Jupiter, we could do it with this system, but we couldn't throw a lot of mass. It'd probably just be, we can put 100 tons onto Mars. We can probably put, I don't know, I'm guessing like 20 tons quickly to Jupiter. And it would take much longer. Jupiter's much further than Mars, so you just wouldn't be able to do it with people because you wouldn't be able to provide, the supplies they need, the oxygen and the food and the water and everything. So I think it's the system that we have in work for Mars would not work to go directly to the outer planets, but if you had a system of depots along the way, you could do it. You'd have to kind of hop along the way. And I don't think you'd go much further than Jupiter. It's twice as far again to Saturn. So and it's just getting so cold. So, but there's a lot of moons on Jupiter, a lot of surface there. So I think that would definitely be a place to go. But as far as sending probes, big probes to the outer planets, absolutely. We could send huge robotic missions to the outer planets. And what I'm waiting for is somebody to start developing these satellites and probes that are, somebody like SpaceX to come along and make it affordable. Like, you guys are all into astronomy, and I'm sure you're huge fans of the Hubble, which was a bargain at a couple billion, or I don't know, what was that thing, 3 billion? And now there's the Webb, the JWST's coming up here, launching in a year and a half, and $8 billion. That's not a deal. I mean, that thing better make it to orbit. That could probably be developed for like 1/10 that cost. So what we need is a SpaceX type contractor to match our low cost rocket. We've reduced the cost of access to space by a factor of 3 or 4, shooting for a factor of 10. Somebody needs to reduce the cost of access to scientific equipment to match what we're doing. So I would love to see that happen. SpaceX would love to do that, but we're kind of busy.
One of our members, Mayank Kapoor, asks, what's it like working for Elon Musk? How is he as a boss? How is he out of the office?
It's quite a trip working for Elon. It's different every day because it all depends on what mood he's in. Like, he's been in a great mood lately. We've been very successful, and Tesla's been doing quite well. So it's been good recently. He's extremely demanding. One thing I tell people often is, I've seen this happen quite a few times in the 15 years that I've worked for him. We'll have a group of people sitting in a room making a key decision, and everybody in that room will say, basically, we need to turn left, and Elon will say, no, we're going to turn right, to put it in a metaphor. And that's how he thinks. He's like, you guys are taking the easy way out, but we need to take the hard way. And I've seen that hurt us before. I've seen that fail, but I've also seen where nobody thought it would work. Many times it was the right decision. It was the harder way to do it, but in the end, it was the right thing. One of the things that we did with the Merlin 1D was, he kept complaining. I talked earlier about how expensive the engine was, and he said, only way is to get rid of all these valves, because because that's what's really driving the complexity and the cost. And how can you do that? I said, well, on smaller engines, we'd go phase shutoff, but nobody's ever done it on a large engine. This could be really difficult. Because we need to do phase shutoff. Explain how that works. So I drew it up, kind of did some, some sketches, and here's what we would do. And he said, that's what we need to do. And I advised him against it. I said, it's just going to be too hard to do. It's not going to save that much. But he made the decision that we're going to go phase shutoff. So we went and developed that engine. It was hard. We blew up a lot of hardware, and we tried probably 100 different combinations to make it work, but we made it work. And I still have the original sketch that I did. I think it was that Christmas 2011 when I did that sketch. And it's changed quite a bit from that original sketch, but it was pretty scary for me knowing how that hardware worked. But by going phase shutoff, we got rid of the main valves. We got rid of the sequencing computer. Basically, just you spin the pumps, the pressure comes up, the pressure opens the main injector, lets the oxygen go first, and then the fuel comes in. So all you got to time is the igniter fluid. If you have the igniter fluid flowing, that engine's going to light, and it's not going to hard start. They got rid of the problem we would have where, like, you have two valves, the oxygen valve and the fuel valve. And the oxygen valve is very cold and very stiff. It just doesn't want to move. And it's the one that you want to open first. If you relieve this fuel, it's what's called a hard start. In fact, we have an old saying that says, and by having sequencing correctly, you can get rid of about, 900 of those bad things. So going phase shutoff made these engines very reliable, got rid of a lot of mass, and got rid of a lot of cost. And it was the right thing to do. Now we have the lowest cost, most reliable engines in the world. And it was basically because of that decision to go do that. So that's one of the examples of Elon just really pushing. He always says we need to push to the limits of physics. Like, an example I'll give is on the car factory. A car moves through a typical factory, like a Toyota or a Chevy factory. A car's moving at, inches per second. It's like much less than walking speed. And his thoughts are that the machinery, the robots that are building the cars should move as fast as they can. They should be moving so fast you can't see them. And he said that's why you can't have people in there, because they just get crushed because people move too slow. So that's the way he thinks. It's like, what are the physical limits of how fast you can make a car? And he looks at videos of like Coke cans being made and things like that where you can't even see them. It's just a blur. And the puck of aluminum, you cut it out of a sheet, you deep draw it, you fill it with Coke, you put the lid on, and you put the paint on it. It's just like it's just like going down the assembly line so fast you can't even see it. And he wants to do that with cars. So that's just the way he thinks. Nobody else thinks that way. And that's why he's going to kill the industry in cars also, because it's just going to make these cars. Basically, you can make 10 times as many cars in the same size factory if you do it that way. And the major cost of the car is not the material in the car; it's a factory that takes to build the car. So that's just the way he thinks. He looks at it from first principles, like, why does a car cost so much to make? Well, you have this gigantic piece of real estate and all these employees in this gigantic building, and you can only make so many cars in this building. You need to make more cars in the same building with the same number of people, and that's what they're working on at Tesla. So yeah, it's pretty trippy working with Elon. It's been really stressful, but really rewarding too. I'm quite proud of what we've achieved. I've always felt like we were way behind schedule and way underperforming because we never got it in time, or it's never as good as physically possible. But it was way better than anybody else could do it, and way faster than anybody else could do it. So we can be proud of that.
Fantastic.
I wouldn't want to have Elon for a father. I think he would never.
Do you guys have a question?
Any other questions?
I have a lot of questions. Well, here's another question from Paige Colley. She says a common misconception about early rocket science was people didn't understand Newton's third law of motion and thought that the rocket fuel needed something to push against. Therefore,
Right.
rocket couldn't travel through the vacuum of space. Is this still a common misconception? And are there any other common misconceptions like that that you try and educate the public on?
Yes. But it's funny. We're in a era of disinformation. I mean, you can find all kinds of people that say the Earth is flat, and nothing you can tell them will convince them that it's not. So there are those people that you don't want to waste your time with them. But I've seen people just say, like, I've seen Quora answers like, they're still saying that rocket engines can work in space when it's clearly impossible because they have nothing to push against, which is just it's so easily provable that it's just it's ridiculous. But think of it this way. This is the way I always explain it to people. If you're sitting in a wagon with a bunch of bricks, and you pick up a brick and throw it out of the back of the wagon, it'll move you, right? You can move yourself by throwing bricks out of the wagon. So you're not pushing against anything, you're pushing against that brick. But the brick's with you. That's what a rocket engine is doing. I'll give you an example. The Merlin engine, the current version of the Merlin engine, basically throws 800 pounds a second of bricks out the back at about 10,500 feet per second. So, if you're throwing 800, pounds of bricks at Mach 10 out of the back of your wagon, you're going to get a lot of thrust out of it. That's how a rocket engine works. And the way that you move that mass is you convert pressure into velocity. And the way that you convert pressure into velocity is with a nozzle. And the more pressure ratio you can have, which is the bigger nozzle you can have, the more velocity you can get out. So when you're in the vacuum of space, you can basically have as much nozzle as you want because you have infinite pressure ratio. You're only limited by the size of the nozzle you can put on the rocket. So once you're in space, you can actually expand that gas to a higher pressure ratio and get more velocity out of it. So you're moving your bricks faster, basically. So it's actually quite simple to explain how a rocket engine works, but people still think that you need to push against air or something, but no, you don't. The air's just in the way.
Okay, here's a fun question from Shirley, actually. She is wondering where you get your methane from.
So on Earth, you get it from high purity wells. There's some in Texas, and various states have high purity natural gas wells. And then you actually we subcool the methane, so it actually will tend to drop out when you do that. The higher carbon compounds drop out. So you want to get rid of the butanes and the propanes and all that stuff in there and just run pure methane. And there's ways to purify it. And on Mars, it's actually quite easy to make. All you need is water and CO2. So you got to find the ice on Mars, and there's lots of ice, subsurface ice on Mars. There's glaciers that are, as far as I can tell, that are several kilometers thick and tens of kilometers long and wide. So if you'd land at one of those sites, you would have enough water to last a giant city for hundreds of years. And then the Mars atmosphere, even though it's very thin, it's about 95% CO2. So you use multi-stage compression pumps to pump the Mars atmosphere up to something you can work with, like say, 3 to 5 atmospheres, 3 to 5 bar. And you take the water and you electrolyze it. You basically unburn it. Water is the combustion product of a hydrogen-oxygen combustion. So it takes a lot of energy to basically unburn it. It's called electrolysis. So about a little bit more than half of the energy you need to make propellant is just decomposing the water back into hydrogen and oxygen gas. Then there's a lot of energy that's used to liquefy it. There's some used to compress the Mars atmosphere, but most of it is to unburn the hydrogen and oxygen. So now you have oxygen gas, very pure, and hydrogen gas, very pure. The oxygen you liquefy, and store in a tank. The hydrogen, you react with the CO2 gas over a catalyst, and it actually is exothermic at that point. You actually get energy out, and you form methane and more water. So the water goes back to electrolysis, and then that hydrogen goes back into the methane reaction, and you take the oxygen and liquefy it. And if you do that, the stoichiometry of water and CO2 comes out at a mixture ratio oxygen to fuel at about 4:1. So for every pound of methane, you get 4 pounds of oxygen, which is perfect because the rocket engine runs at 3.6, 3.5 or 3.6. So you have excess oxygen, which people can breathe, and the rest is used as propellant. So it works out quite nicely to make the propellant on Mars. It takes a lot of energy. If you try to do it with solar, it's going to be extremely difficult, but it's doable. To get one ship back, you'd need about 8 football fields worth of solar cells on Mars, and you have to keep the dust off them. So that's tricky. It's much better to use a nuclear reactor, a fission reactor. It's more compact. You actually get more. You get more power out per pound of reactor than you do out of solar cells, so it's more mass efficient. If you're going to take it to Mars, it's more efficient to ship reactors than it is solar. It's just that nobody's really developed a space reactor yet. We're working with NASA on that. Hopefully they'll get funding to develop. They have a program called Kilopower going, which is like a 10,000 watt, a 10 kilowatt reactor. We need, a megawatt, but you got to start somewhere. Eventually, the right way to have power on Mars will be fission, but initially it'll probably be solar. But in order to get the rockets back, we need a lot of power there to make propellant.
Okay, here's another fun question. Does SpaceX have any protocols in place in case signs of previous life are found on Mars?
I'm sorry, I didn't quite get that.
Does SpaceX have any protocols in place in case signs of previous life are found on Mars?
Well, NASA has protocols for that, which we're following initially. Yeah, we want to go there and explore and find the signs of life. It's very possible that there is life there. Probably microbes in the dirt, and there probably was a lot more when Mars was wet. So there'll probably be signs of previous life. I think Robert Zubrin explained it quite well, that how overblown this, not mixing the biology is, in that when, one of these anthrax poisoning cases happen, they can tell exactly which lab that anthrax came from by looking at the genes. So if you're trying to tell, Earth life from Martian life, you look at the genes, it's going to be very easy to determine that. So I think it's way overblown, but we want to do exploration first before we do colonization, and at that time, humans there are going to have a much better chance of digging up and finding where the life is. If it exists there, if it did exist, I think the best way to do it is to put humans there. In the meantime, they should be sending more robotic missions. I think that they should be doing 10 times as many robotic missions as they're doing. And doing, way more focused on trying to find life, because I think that's a huge, really important to answer. And I'm all for going to Enceladus and finding life in those oceans. It looks like, these ocean planets or ocean moons can support life. We need to go find out. It's probably it'd be much easier to do that robotically, to go to the moons of Jupiter or the moons of Saturn to look for life. So we need to send missions to do that.
Okay, so this is going to be our final question.
Okay.
Where is it? Oh, I lost it. Wait, hold on. Okay, many of us look up to you as a role model. Who do you find inspirational?
Who do I find inspirational? Elon, of course. I mean, he's a huge influence on me. When I left TRW, I thought if we fail, which was was at the time I thought was a high probability because nobody had ever done this, and I thought I'll just go back to TRW. So I didn't burn any bridges, but once I learned how he thought and how he operated, and I became an entrepreneur. He influenced me so much that there's no way I could go back to working for a big bureaucratic company like Northrop Grumman. So it was quite profound, and the way that I deal with life, I think much differently now, just because of the Elon influence. I live a lot bigger. I make bolder decisions. I take higher risks, and I'm not this conservative TRW engineer that I was when I first met Elon. I'm an entrepreneur. So obviously he's probably my biggest influence for sure.
Very nice. Well, all of us are so excited that you called, and we just want to give a huge thank you. I don't know if we want to talk about it.
Thank you. I'm always glad to talk with fans. As you know, I'm a member of the LA Astronomy Society. I'm hugely into astronomy. I always was as a kid. I think I have one of these minds where nobody can really fathom how big space is, but I'm one of the people, and I'm sure many of you are that way too, where I can fathom how unfathomable space is. And one of the things that I always thought about is every planet and every moon we went to in the solar system was like a wow factor. There's just so much there, like just Pluto recently. There's so much more there than anybody ever thought. Imagine what's out in the universe, at other star systems and other galaxies. It's just, you can't imagine. It's incredible. And it pains me that we're confined to Earth, and I'm trying to fix that as fast as I can.
Yeah. In the meantime, we have nice pictures to look at of space. All right. Well, thank you so much.
Thank you.
Let's all give one giant round of applause.
Again.